Hello, hello. So today we're solving two by two linear, homogeneous, constant coefficient systems of differential equations. Um, it turns out in the case in that very narrow class of problems, right? So we're looking at two by not just general systems, but two by two linear, constant coefficient, um, homogeneous. These in that class of problems. Dimension two, there are basically only three things that can happen. So I'm going to do one of each. And notice it's really sensitive. The three different algorithms that you need are, the problems can look almost identical, but they can require a totally different algorithm. I mean, look here, all that is different between these three problems is just that one term, whether it's a zero, one, or a minus one, the coefficient on that y, right? So I have three different systems here. And now, um, just with a zero, one, or minus one on that one term, it's going to dictate three different algorithms. So, um, what's so special about linear, homogeneous, constant coefficient, right? Well, all of those can be rewritten in matrix vector form, right? So for all of these, call vector x our vector of unknown functions, y, x of t, y of t, and then once you do that, you could rewrite all of these in matrix vector form, right? So this is dx dt equals 1, 0, minus 1, 1, x, right, is the equivalent um, matrix problem, right? This one becomes what? This one becomes dx dt equals 1, 1, minus 1, 1, x. And this one, there we go, becomes dx dt 1 minus 1 minus 1, 1, x, right? So that's just getting everything in matrix vector form. And once you do this, then it's the eigenvalues that really dictate what next step we take is, right? So in this phase, we were just saying, okay, convert everything to matrix vector form, right? On this next step, we're going to take everything and we're just going to get the eigenvalues, right? That's our next step there. So let's take each of these and get the eigenvalues for that matrix. And when we do this right here, I'm just going to do determinant a minus lambda I, set it equal to 0 in every single case. So here, I'm going to have what the determinant of 1 minus lambda, 0 minus 1, and 1 minus lambda. All right. So when I set this equal to 0, I just get 1 minus lambda squared equals 0 because I subtract 0 times minus 1, which is 0. So this gives me a repeated eigenvalue. I have lambda equals 1 with multiplicity 2, right? Here, what happens? I have the determinant 1 minus lambda, 1 minus 1, 1 minus lambda, right? I'm going to set that equal to 0. So now I get 1 minus lambda squared, and here I get plus 1 equals 0, right? Because I have a, um, on the off diagonal, right, I have a negative of it. Um, it's already negative, and I subtract again, right? So what does this become? This becomes, right, I subtract the 1, I can square root both sides, and I can subtract the 1 and negate both sides, right? So this gives me complex roots. This last one, what do I have here? I have right, 1 minus lambda squared minus 1. And here, if you FOIL this out, you're going to get 1 in front, right? But that 1 is going to cancel with this minus 1. So we get a nice easy factorization. We get just lambda times negative 2 plus lambda 0. So lambda is 0 or lambda is 2. Right? So there we go. We have three very different stories with regards to the eigenvalues, right? So this is going to be the repeated eigenvalue case where we are going to use matrix exponentials. Right, this is the distinct real eigenvalue case. So we're going to use C1, our solution is going to look like C1 e to the lambda 1 t v1 plus C2 e to the lambda 2 t v2, where lambda 1 and lambda 2 are the eigenvalues and v1 and v2 are the eigenvectors, right? So that's how we're going to get our solutions there. And I should say in this first case too, how we're going to get our solutions. The general solution, when you have repeated eigenvalues, it's going to be linear combination of the columns of e to the at, right? That is the general solution in that case. Then in the middle, we have the complex. So what do you do here? Here, you calculate, it looks a lot like this actually at first. So you start with e to the lambda t v, where v is an eigenvector for lambda, right? And typically, honestly, just pick the positive root and throw away the negative. It's a lot like characteristic polynomial method for solving higher order d's. You don't need to do both the plus and the minus. Just pick one or the other, probably the plus, right? And calculate this, and then the general solution is the set of all linear combinations of the real and imaginary parts, right? So split using Euler's identity, split it into real and imaginary parts, right? You have some sines and cosines. And that's what will give you the linear combinations of that real and imaginary part. Will give you your general solution, right? So these are the three techniques, and each of these examples calls for exactly one of these techniques. So let's show each of these. So I'm going to start actually with system 3 because it's probably the cleanest. So for system 3, what would you do? We have already our eigenvalues. So let's carry this out for system 3. So for our eigenvalues are lambda 0 and lambda 2. So for each of these, find an eigenvector, right? Find an associated eigenvector. So here's A is 1 minus 1. There we go, minus 1, 1. All right. And I want this times xy equals lambda times xy. But in this case, lambda is 0, right? So I want this to be 0, 0. So this tells me that I want x minus y to equal 0, and I want minus x plus y to equal 0. So we just need that y equals x, right? Those two equations are the same. So a perfectly good, let's call this lambda 1 is our first eigenvalue. Perfectly good eigenvector would be 1, 1, because I just need anything where y equals x, right? Then lambda 2 equals 2. Let's consider this other eigenvalue. So what would this be? 1 minus 1 minus 1, 1. Xy equals 2xy. So what does that tell us? That tells us that x minus y equals 2x. It also tells us that negative x plus y equals 2y. Right? And then these are the same equation, basically, right? These both, if you simplify a little bit, both become what? This says, these both say that y equals negative x, right? Yeah, yeah, these both say that y equals negative x, right? So again, just pick something simple where it does. So say 1 minus 1. Right? So there we go. There are the eigenvectors for those eigenvalues. So now I can say what the general solution to that system is, right? The general solution is going to be what? C1 e to the eigenvalue times the eigenvector plus C2 e to the eigenvalue times, again, eigenvector, right? So if you want to then rewrite that as our actual functions, x of t and y of t, what do we have? X of t is just c1 plus c2 e to the 2t, and y of t then is c1 plus, sorry, minus c2 e to the 2t, right, for c1 and c2 in the reals. There we go. So there's system 3, right, using the e to the eigenvalue t times eigenvector as the form of our solutions. Okay, now let's do system 2, right? So system 2, what do we have? We had this lambda equals 1 plus I, right? Let's use that as our eigenvalue. Let's solve for an eigenvector. So what is our matrix here? Our matrix here is 1, 1, minus 1, 1. So take that times xy. We want that to equal 1 plus I times xy. So what do I end up with? X plus y equals 1 plus I x. And we also get that negative x plus y equals 1 plus I y. Right? And again, if everything worked out, all right, then we have, we're going to have that these two equations are dependent, right? So what happens in the first one? The first equation, we just get y equals ix, right? Because the x's cancel if you distribute there and there, right? In the second equation, what do we get? There the y's cancel, so you get negative x equal I y, which is good because these are actually the same equation. If you multiplied the first equation by I, you would get exactly the second equation, right? So this is good. Now, as far as an eigenvector, let's just pick, say, y to be 1, so that then when you, or sorry, let's pick x to be 1, so that y then is I, right? But if you put in a 1 right here for x, then you get I for y. So there we go. So there's your eigenvector. From here, what happens? Well, we're going to have e to the, so the solutions are going to be e to the eigenvalue t times eigenvector. And then we're going to split using exponent properties, then split using Euler's. So we get e to the t cosine t plus I e to the t sine t in that first component, right? And the second component, what do we have? We have e to the t cosine t I, right? And then I have e to the t sine t I squared. Okay, so what are the real and imaginary parts? Well, the real part here is going to be e to the t cosine t negative e to the t sine t. The imaginary part is anything that has an I on it, right? Notice here we're doing the fact that I squared equals -1, right? So that's where that's coming from. Now for complex solutions, like I said, the real and imaginary parts of a complex solution, they become a basis for the real general solution. So the general solution of the reals, it becomes what? It becomes that x of t equals c1 times the first vector plus c2 times the second. So there we go. There's the general solution, right? And if you want, again, you can get it back in terms of x and y by just ripping out the first coordinate. And the second. There we go. So there's our general solution for the x of t and y of t. Now, finally, the last case, let's look at system one. Here we have a repeated eigenvalue. So let's calculate e to the at, which there's a very specific trick as to how to do that. You want to add and subtract lambda I, right? Where lambda in this case is just 1, right? We'll do 1i, subtract it, and 1i add. Right, so I get a oh, sorry, and I want actually t's here. There we go. Yeah, that's better. There we go. Right, so this is the little trick is to add and subtract lambda I, or in this case lambda it, right? Because you want to factor a t out. Why is this helpful? Well, because here I claim that now if we use the power series on each of these, it's much more manageable than it was before. So what is a minus lambda I on this system one? On this system one, it's actually going to be 0, 0, minus 1, 0, right? This is the first system. Right, so there's that first e power series with a minus lambda I t plugged in. There we go. Right, now, here's what's nice is this matrix, and everything after that all goes to 0, right? So this first one is literally just what? 1, 1, 0, t, and 1 is that first. Now, what's the second? The second is of e to the it. So this is going to be, again, infinite series based on the e power series. And here, notice we're putting 1 it into There we go. So if you look at these, what ends up happening over there? Well, on the right, you end up getting exactly the series for e to the t in the top left, exactly the series for e to the t in the bottom right. And from here, this actually ends up having the same effect as a scalar. Um, right. So if you do the matrix multiplication, that's what you end up with. So this then, like we said, the columns of this give you the basis for the general solution. So what's the general solution? The general solution then is x of t equals c1 e to the t e to the t times t plus c2 0 e to the 2. There we go. So there's our general solution in the third case, right? So there we go. Now we have all three solved. And again, if you want, you could rip this apart into just x and y. So there's the general solution back just in terms of x of y, right? Here I really wanted to demonstrate the matrix exponential. Notice though the system is decoupled, right? So you could actually do this with integrating factors. What do I mean by that? This is not something I'm going to do here in this video, but it's worth an exercise. So on your own time, try this. Ignore the second equation and just solve this, right? What are you going to get? You're going to get, and there you could do separation variables or integrating factors, kind of whatever. You're going to get this when you solve it, right? Then take that C1 e to the t and plug it in here for x, right? After you get that C1 e to the t, plug it in there. And then you could solve the second equation by integrating factors. And it'll actually give you the same thing as you had here. So yeah, just note that this particular one is decoupled, but I wanted to show this method because this method worked whether or not the system is decoupled. And decoupled means just that only one of the variables shows up in its own equation. Right? So, all right, great. Well, there are the three algorithms for 2x2s. Hope that was useful. Enjoy.